Hello, nonlinear students. This is another lecture on exponential functions. This time we are going to be studying exponential decay functions. The last lecture was on growth functions. That was things that were growing exponentially like this. In 7.5, we're going to be studying the decay models. I have that visual here again. Here's our exponential growth models. Remember, they didn't do much for an extended period of time, and then they started to kind of pick up speed and grow faster. Exponential growth functions were written like this, and y equals a times b to the x. That's going to be the same for exponential decay functions, only with growth functions, the b value was always bigger than 1. So it could be like 1.1, or it could be 5, but it has to be bigger than 1. With an exponential decay function, the b value is going to be between 0 and 1. Can't be negative, but it can be between 0 and 1, something like a half, or even something like 0.9 would work. But it's got to be between 0 and 1, and that's going to cause us to decay or decline rather quickly, and then eventually level out. In reality, if you understand section 7.4 very well, you're going to find 7.5 fine as well. There's nothing really that's more difficult or anything like that. It's just a different type of exponential function. So remember, exponential functions look like y equals a times b to the x, where a is the value of y when x is 0. That's still going to be true. The value of a is going to be whatever y is when x is 0. And b is the number that the output is being multiplied by. Now, this is a little bit harder to get sometimes with an exponential decay function, but I'll show you a trick for that really. That makes it pretty easy. An exponential decay model, remember, this was like you have an investment of some sort and it's growing at a certain rate was the growth model. That was from last lecture. Now with the decay model, the difference here is that this is going to be a subtraction sign rather than an addition sign. This should say decay, where a is the initial amount, r is the decay rate. It's not growing now, it's decaying, and t is still the amount of time. One of the tasks that you guys are going to have to do is I'm going to give you a table and expect you to come up with the equation. Remember, exponential functions, both growth and decay, are written y equals a times b to the x. A is going to simply be the y value when x is 0. That's still true. That's still pretty easy. So we're going to say y is equal to 1 times. Now b is whatever you're multiplying by to get to the next term. What do you multiply 2 by to get to 1? What do you multiply 1 by to get to 1/2? If it's truly exponential, it should be the same every time. The way that I'm going to tell you to get this is to divide a term by its previous term. Okay, I'm going to say that one more time. Divide a term by its previous term. So here you have the number 1, divide that by 2, you get 1/2. Take 2, divide that by 4, you still get 1/2. What do you think 1/2 divided by 1 is? It's still 1/2. 1/4 divided by a half, 1/2. Okay, when you get that constant number, that same number every time you do that, that is going to be the decay rate. Take a number divided by its previous term. I would write that in my notes. To get the b term, take a number and divide by its previous term. That will always work. So we're going to get y equals 1 times 1/2 to the x. We don't really even need to write this one. We'll often write this as just 1/2 to the x. Why don't you pause it here, go ahead and try this one. It should be very similar for you. Exponential functions are written y equals a times b to the x. We know what the a is. We just look at the table. When x is 0, it gives us the a value. So this is going to be 1/2. And the b term is going to be, remember, whatever you're multiplying by to get to one term to the other. If it's difficult to see, take a term and divide it by its previous term. What is 1/2 divided by 2? You're going to get 1/4 when you do that. What is 2 divided by 8? You're going to get 1/4 when you do that. You could try 1/8 divided by a half. You're going to get 1/4. So that's the b term. And you can just write that in. Y equals a times b to the x power. It's not true to multiply these things. Sometimes people try to do that, they get like y equals 1/8 to the x. That's not true because only the 1/4 is being taken to the x power. If you multiply those, that's implying that both were being taken to the x power, and that's why that's not true. We are also going to have some questions where you are expected to graph the function. Remember, this is going to be just the same as growth. You're going to take the equation, and you're going to make a t-table, -2, -1, 0, 1, and 2, and you're going to fill it in. Some of it's really going to be easy to see. We know that anything to the 0th power is just 1. And 0.3 to the first power is just going to be 0.3. But we can use our calculators to fill out the rest of this. 0.3 to the second power is 0.09. 0.3 to the negative first power is 3.3. And 0.3 to the negative second power is 11.1. So we should be able to graph this. 0, 1 would be here. 1 1/3 would be there. 2 1/9, that's even smaller, or 0.09, that's even smaller. -1, 1, 2, 3, that would be about here. And -2, 11, that's somewhere way up here. So what this is looking like is this. Okay, and that does fit what we expect the exponential decay models to look like. Remember, they decline rather quickly and then they level off. Great place to pause it and try one here. You guys should be able to do this question. This can be, at least, a calculator question. 4 times 1/2 to the 0th power is 4. We know that because 1/2 to the 0th power is 1, and 1 times 4 is 4. 1/2 to the first power is 1/2, and 1/2 times 4 is 2. Once again, you should be able to type this in your calculator and get the right answer. 1/2 to the second power is 1/4, and 1/4 times 4 is 1. If you did 1/2 to the negative first power, remember 1/2 to the negative first power is going to cause this to flip, essentially be 2/1 to the first, and 2/1 to the first is 2. You don't need to do all this. You can just type this into your calculator. Either way, you're going to get 8 here. You probably can pick up on the pattern here as well, leading you to get 16 there. Go ahead and plot them. 0, 4, 1, 2, 2, 1, -1, 1, 2, 3, 4, 5, 6, 7, 8, and 2, 16. That's way up here. Boom. Right? Worth noting that this line is going to get forever closer to this axis, but it's never going to cross it. I have 2 word problems for us to do, and then we're going to be done. So remember, this is the exponential decay model. A is your initial amount, R is the rate by which it's decreasing, and T is time. So we buy the new iPhone 12 Pro for $1,100. $1,100 is going to be our A value. So when we write this equation, it's going to be y is equal to 1,100. The rate by which it's decreasing is 28%. We need to turn this into a decimal, which would be 0.28. So we would have 1 minus 0.28 to the t power, and we see our t, it is 3 t is time. We can simplify in the parentheses. We would get y is equal to 1,100 times 0.72 to the third power. And our calculator will be able to handle this all in one line, at least most of the calculators, if we're using the level that I recommended at the beginning of the year. We can type in 1,100 times 0.72 to the third power and get $410.57. So we bought our iPhone for $1,100. 3 years later, it is $410.57. Here's another type of these questions. A lot of times the book throws this type of question at us, and I think it's maybe a little bit harder to, defer what it's, or identify what it's saying, so I thought I'd throw one of these in here as well. So the number of acres of pine forests are decreasing between the years of 1963 to 2002 by 0.85%. In 1963, there were 41 million acres. Write a function that models the number of acres. So students will do different things for this question. Remember, our formula is going to be y equals a times b to the x, or specifically because we're using the exponential model, a 1 minus r to the t. I just want to point out that the a value is still going to be the a value, and b here is going to be whatever 1 minus r is. So it's still an exponential model. It's just a little bit more, tangible because we know what r is, a and t would be. So we need to start filling in the answers. I'm going to leave 41 as a. I'm not going to write 41 million here. And the reason I'm going to do that is at the end, I'm just going to write whatever our number is, million, and that's going to work. So 41 goes there. 1 minus the rate. Well, the rate is in a percentage. It's 0.85. We need to turn that into a decimal. And so we're going to move the decimal place over twice. It's going to be 0.0085. This is 0.85% as a decimal. So we're going to have 1 minus 0.0085 to the t power. We can do 1 minus 0.0085. 1 minus 0.0085, and we're going to get 0.9915. This is the model that would describe the situation. 41 times 0.9915 to the t power. Now we need to figure out how many trees there are going to be in 2002. So we are going to plug in whatever 2002 minus 1963 is, because that'll tell us how many years it's been. 2002 minus 1963 would be 39 years. So I'm going to plug in 39 for t. We would get y is equal to 41 times 0.9915 to the 39th power. We can type this into our calculator, 0.9915 to the 39th, and get 29.39 million acres. So that'll be our answer to this question. Please let me know if you guys have any questions, and I'd be happy to go over this with you.